This is video 7 in the AC theory unit, and we're going to look at parallel calculations. Now here we've got a parallel circuit with an inductor in parallel with a resistor across a 230 volt supply. And we're going to find the currents in the inductor and the resistor and the phasor sum of those currents. The current flowing in the resistor is simply voltage divided by resistance, so 230 divided by 20 will give us 11.5 amps flowing in the resistor. The current in the inductor, similar to that, V over XL gives us 230 over 10, which gives us 23 amps. The phasor sum of the currents in the branches and the supply current, well, we can find that by drawing the reference, which will be the voltage, because the voltage is constant in a parallel circuit. We can draw the scale of 1 centimeter equals 4 amps, and so we can draw the resistive current along there, 11.5 amps. Remember, resistive current will be in phase with the voltage. The inductive current will lag the voltage reference, because in an inductor the current lags behind the voltage, and that's 23 amps along there. The resultant of the two will be the supply current, so we can draw the parallelogram, we can find the resultant, find that by using the scale, and we get IS, supply current, is 25.8 amps. We can calculate that to verify the graphical representation. Our resistive current squared plus our inductive current squared, all square rooted, will give us 25.71 amps, which is very similar to our graphical representation. To find the impedance of the circuit, we need to transpose our formula that I equals V over Z. That's our basic current formula in an AC circuit. So if we transpose for Z, Z is equal to V over I. So Z is equal to 230 divided by our current, which was 25.71 that we just found, and that gives us an impedance of 8.95 ohms. So that's the total opposition to current flow in that circuit. The power factor of the circuit, now if we look at the phasor diagram, we've got a resistive current of 11.5 and we've got a supply current of 25.8. Our power factor in a parallel circuit is that resistive current divided by the supply current. So it's 11.5 divided by 25.8, which gives us 0.4457. The angle of the circuit is going to be the inverse cosine of that 0.4457. So the inverse cosine of that gives us 63.53 degrees. And we know it's lagging because it's an inductive circuit and our phasor current was drawn down. There's our supply current there, and we can check with the protractor, and that gives us just over 65 degrees. Here we've got a capacitor in parallel with a resistor, so we're going to go through the same process, but we're going to be using the capacitive reactance. So first off, we're going to find the current in the resistor, which will be 230 divided by 15, gives us 15.33. The current in the capacitor is going to be V over XC. XC is 12, 230 divided by 12 gives us just over 19 amps. The phasor sum, we're going to draw the reference as the voltage again, because the voltage is constant in a parallel circuit. I'm going to use the scale of 1 centimeter to equal 4 amps. Here's our resistive current in phase with the voltage, 15.33 amps, and our capacitive current, which leads the voltage, 19.17 amp. Make the parallelogram, find the resultant, and I get 24 amps graphically. If I want to check by calculation, I square both the currents, the resistive current and the capacitive current, take the square root, and that gives me 24 0.55 amps. Very similar to our graphical representation. The impedance of the circuit, again, we transpose for Z. Z is V over I. We've got 230 divided by 24.55. 24.55 was our resultant current, and we get an impedance of 9.37 ohms. Power factor, again, is going to be IR over IS. 15.33 divided by 24 gives me 0.639 leading. And it's a leading circuit because it's a capacitive circuit, and that supply current is in front of the resistive current, in front of the voltage reference, because remember the phases go anti-clockwise. The phase angle is going to be the inverse cosine of that 0.639, which gives me 50.28 degrees. And here's our phasor diagram again. We can check that with the protractor. Gives me just over 50 degrees. If we have all three in circuit, like the series circuit, the inductor and the capacitor are going to be working against each other. So we work out the current in the resistor again. V over R gives me 4.6 amps. Current in the inductor, V over XL, nearly 3 amps. Current in the capacitor, V over XC, 5.75 amps. Now when we draw the phasor diagram, we're going to have the two currents in opposition to each other. So as our voltage again as the reference, the resistive current in phase of 4.6. IL is going to be lagging the voltage by 90 degrees, and that's 2.875. And our IC is going to be leading the voltage, and that's our 5.75. Now you can see the IC and the IL are in direct opposition to each other. And so the sum of those two is going to be IC minus IL, because IC is the bigger one, and that's going to leave us 2.875. It's just coincidence that it's the same value as the inductive current. There's our 2.875 there. That's the resultant of this IC minus IL. And we can find the resultant now by drawing the parallelogram and finding the hypotenuse of the triangle that's formed, and that gives me a supply current of 5.4 amps graphically. Let's calculate that. We can find the difference between IL and IC. There's our 2.875 squared plus 4.6 squared all square rooted gives me 5.42. The impedance of the circuit, again, we transpose for Z. Z is V over I. 230 divided by 5.42 gives me 42.44 ohms. Power factor, IR over IS, 0.852. Leading, because remember the capacitive current was bigger than the inductive current. And I can find the phase angle by doing the inverse cosine of that 0.852, gives me 31.57. I can check the angle on the diagram, on the phasor diagram of our protractor, and there we're on about 31 degrees.